Hello everybody, I will start my today another live coding session. So today I solve this question. Binary search tree iterator implements a BST iterator class that represents an iterator over the inorder traversal of a binary search tree. So iterator class constructor takes root node and initializes an object of the BST iterator class. The root of the BST is given as part of the constructor. The pointer should be initialized to the non-existing number smaller than any element in the BST. Okay. Boolean has next. Returns true if there exists a number in the traversal to the right of the pointer. Otherwise, return false. Okay. And next method moves the pointer to the right, then returns the number as the pointer. So this iterator should iterate, or should say traverse the numbers of the given binary search tree in the constructor, in ascending order. Notice that by initializing the pointer to a non-existing smallest number, the first call to next will return the smallest element in the BST. You may assume the next calls will always be valid. That is, there will be at least a next number in the traversal when next is called. I see. And as the follow-up, could you implement next and has next to run in average constant time and use O of H memory where H is the height of the tree? Okay, so this follow-up, constraint suggests that I cannot create the list. So the first intuitive idea of mine is that in the constructor, I create the list of the numbers and I just have to traverse the iterator on that list. But this isn't possible because in the end, I can use only O of H memory. Yeah. Okay. So let me clarify my understanding of this question first. So as the interface, interface is as specified. And I'd like to confirm if root can be null or not. And I check it and they find that there is at least one node, so root is not none. Okay. And the given tree is the binary search tree. Good. Okay. So let me take a look at examples. So let's say I'm giving a binary search tree like this. So okay. In the binary search tree, when I do the in order traversal, the nodes I visit is sorted in ascending order. That's the binary search tree. Like 1, 2, 3, 4, 5, 6, 7. I'm traversing in order traversal, and I find that the nodes are in ascending order. Yes. So this is binary search tree. So at least the first node, first tree, the pointer should be somewhere, nowhere. And when I call the next method, the pointer should point into here, the next pointing to here, the pointing to here, in that way. Okay. And as I said, the brute force approach should be firstly, in the constructor, I will do the binary search, the traversal, then put it in the list, but it takes O of n time compressed, no, O of n space complexity, assuming that there are n nodes. So I have to think of a better way. So actually, I know how I can do the inorder traversal in iterative way. or in recursive way. So in the recursive way, the binary search, it should be look like this. Then here, C root dot left, then call inorder root dot right. But something I have to take care is that once I visit the, left child tree, I have to come back to the current root node. So I have to keep track of this root node so that I can come back after. So after I traversing 1 to 3, I have to come back to root 4. Yeah. But obviously, root 2 doesn't have the pointer to root 4. So I have to take care how we can do it. Yeah. So I think it isn't realistic to use the recursion here because every time I call the next method, I have to pause the traversal. And then next time the next method is called, I have to continue the traversal from where I left. So let's think of the iterative way. So in an iterative approach, I use the stack and basically also I keep track of the current node like this. Firstly, it should be root. Then while current is not none, or I will write it down here and I will copy paste it later. So if there is something in the stack, I continue. So if current is none, current is not none, I move the pointer to left and I append it to stack. So in this way, when I'm at here, root 4, I go down to root 2, root 1, and 4 to 1 is appended to the stack in this way. Then current reaches none. And at this point, because root is none, I go out of the loop. And what I will do is pop out something from the stack. And exactly, this is something I should see here. In this case, 1 is took a look. Then I move the current pointer to current.right. So I took a look at the 1, and then current.right is none, so current is now none. And I come back to line 28, because current is none, I go to line 32, and I pop out something from the stack. So now what happens is 2 is popped out. Sorry, this should be current. Yep. So now 2 is the current node, and I take a look at current here. Then current is moved to current.right. Then it is 3. And from 3, because current is not known, I go to line 32, and I pop out. With me? No, at 3, node 3, because current is not known, this 3 is appended to the stack, and 3 is appended. Then current is current.left, so it should be none now. In that way. Actually, this is a kind of template I have in my mind, and I will use it in this implementation. Okay. So in this way, let me take a look. On average, it should take all one time and use all of H memory where H is the highest, height of the tree. Okay, so this is met because next method, so I can say I keep track of the self.current, self.stack. And as I've written here, I can do traversal, continue traversal, as long as this is met. So checking this, run 227 takes only the constant time. So has next takes only the constant time. And next, this on average takes only the constant time. Because in the end, I traverse all the nodes. Let's assume there are n nodes. N nodes in n n method calls. So on average, it takes only the constant time. N divided by n is 1. Okay. And the memory. So stack can have up to O of 8, which is the height of the tree. Yeah. And yeah, that's it. Because yeah, obviously when I put all the trees height, then when I put 1, 4, 2, 1, there's no tree. No, there's no node as the child of this node 1. So I pop out node 1 from the left of the stack. And instead, in the end, I put node 3 here into the stack. In that way, the stack can have up to the number of nodes, which is equal to height, max height. Okay, so I'd like to say I meet this follow-up constraint. Okay, so now I will implement. So for this next method, I copy this. So now I have to make this self.current. And the stack should be self.stack. Okay. So here I should return this one. So after moving the self.current, I return this self-read. Maybe I should call it temp. Okay. So let me walk through my code. Yep, I will try this. 1, 2, 3, 4, 5. Stack is empty first, and current is pointing to none first. Oh, wait, the problem is first 3, I start with none and empty. Maybe I should start with root. The first 3 should be node 5. Okay. In rise 62, self.current is not known, so I go to rise 63, and self.current is not known. Yes. So I put this self.current into the stack, so node 5 is pushed, then current goes to self.current to the left. Then again, I continue this. 2 is pushed into the stack. Yes. And now 1 is pushed into the stack. Then current is now pointing to none. So I come back to line 63 and go out of the loop and go to line 67. Self.current is self.stack.pop. So now current is pointing to node 1. And this is stored as temp. And self.current is self.current.write. So this moved to here. Then I return node 1. So first 3 returns 1 first. Yep. Then I come back to line 63 and I do the same. Current should be pointing to none and 3 should be pushed into. Then no. 3 is actually the child of 4, not the child of 1. So this isn't correct. This shouldn't be pushed into. Either I don't push anything, but next, in line 70, current should be pointing to none. So next in line 64 and line 65, current is none. I go to line 69 and self.current is self.stack.pop. So current now takes record 2. Then temp is equal to self.current and I go to line 71 and current is current.write. So it goes here and I return temp, which is 2. Okay. So I do the same from here. Current moves here and here. And in that process, 4, 3 are pushed into the stack. And then, now current is here. Because current is none, I go to line 69. And 3 is popped out. And we should be returned. And current is now pointing to this here, which is none. Yeah. Then because this is none, after in the next method call, I pop something from the stack and I get 4, which should be returned. Yeah. And current is now pointing to current. Right, which is none. Yeah. So this is it. Wait. Do I need line 64? Why? No, I don't need this. I have to do it only once. And it is guaranteed that this is met because I have at least one node to be visited when next method is called. Yep. So I don't continue this anymore, but I'm pretty sure this is correct because I covered all the lines. And actually, this isn't a good example because I visited 3 in 1, 2, 3. Oh, yeah. No, it's okay. Okay, so I covered those lines. So let me execute my code. Okay, so I submit my code. So what's the problem here? So I see. So I have to return the value. So I return this. And this should be self.stack. Self.current. Good, accepted. And accepted. Great. Okay, so let me quickly wrap up. So today I solved the question, binary search tree iterator. So in this question, I'm given binary search tree as the constructor. So I will construct the class, iterated class. And just like the typical iterated class, it has the has next method, which returns the boolean, and next method, which returns the next value. Yeah. So, and to implement this, I use the inorder traversal in iterative manner. So I use the stack and also current pointer, yeah, inside of this class. Yeah. And I couldn't use the recursion here because if I use the recursion, I have to keep calling the recursion until the end. It's not possible to stop the recursion in the middle and then resume it later. So I use the iterative, the traversal. Yep. So that's it. Okay, that being said, I finished my today's coding practice. Thank you so much. Bye.